of AP Chemistry. We've only got 3 more units left in the school year, so super excited to continue making great progress towards our goals of achieving 3s, 4s, and 5s on the AP exam. So today we're going to start off with a little bit of a different topic. We're going to talk about equilibrium today, maybe a little bit of a new topic for you guys, but I'm super excited to get into this. There's some really cool stuff that we can do mathematically with some of the equilibrium constants, and today we're going to introduce the wonderful world of ice tables. Oh, you're going to love them, so let's move on. So hopefully by the end of this video, you will be able to explain the concept of chemical equilibrium, understand the concepts of reversible reactions. You should also be able to explain the concepts of K and Q and know how to calculate these values. And I know you don't know what K and Q are at the moment, but you'll find out shortly. And then evaluate K and Q to determine reaction direction towards equilibrium. So lots of different stuff we're going to look at today. We're going to start with some theory, and then we're going to dive into some math here in just a little bit. So to think about equilibrium is to be in a state of balance. Think of it kind of like a tug of war. You've got people pulling on both sides. Well, equilibrium occurs when the amount of strength of pull in the tug of war on the left side is the same as what's on the right side. It doesn't have to necessarily do with the number of people. It has to do with the rate at which the individuals are pulling. And chemical equilibrium works the same way. Many chemical reactions don't just go from reactants to products. Some will proceed slightly towards the products. Some will go nearly completely towards the products. And sometimes the chemical reaction will work in the reverse direction. Now, most chemical reactions that we've looked at has a single arrow. In this instance, though, we're looking at reactions that have a double arrow. That is, there is a reaction that is going from reactants to products, as well as one that is going from products back to reactants. Chemical equilibrium occurs when opposing reactions proceed at equal rates. The key thing here to keep in mind is that the reaction is not static. Equilibrium does not occur when the reactants and products are the same, nor does it occur when the reaction stops. The equilibrium occurs when opposing reactions proceed at equal rates. So that's something to kind of keep in mind here. We're not looking at the amount of reactants versus products. That can be completely different. But the rate of the reaction going one direction is the same as the rate going the opposite. We take a look here. There's an example of an equilibrium state. We start off with N2O4, and it proceeds to 2NO2, but it also proceeds backwards as well. And the reaction is at equilibrium when the rates, that is the amount of reactant going to product and the amount of product going to reactant, is the same. So if we take a look at the example here, we have the example that we used previously, and we're going to consider the rate laws for both. So we have a forward rate as well as a reverse rate. Now at equilibrium, remember the rates are going to be the same, so we can set them equal to each other. Based on this information, if the rates are the same, we can get a constant value if we know the concentration of NO2 at equilibrium and the concentration of N2O4 at equilibrium. So keep in mind, at equilibrium, the concentrations no longer change. Okay, they may be different from one another, but they no longer change. But the rates of the reaction going forward and reverse are equal. And the diagram to the left shows this really well. The forward rate and the reverse rate of the reaction eventually become equal to one another. That is equilibrium. The amount does not change either. However, they may not necessarily be the same. It depends on the equilibrium constant and whether the reaction goes completely towards products or only some of it towards the products. So how do we determine the equilibrium constant? Well, the equilibrium constant, Kc or Keq, is described in the reaction below. So if we have a reaction where we have a coefficient of A and A as our chemical, a coefficient of B for compound B, C for C, D for D. Okay, remember all the lower cases are coefficients, and then all of your chemicals are uppercase. It's basically if the concentration of your products divided by the concentration of your reactants. The other thing to keep in mind is that your coefficient actually becomes a subscript. It becomes an exponent when you go through and do this. So for example, if we look at the Haber process below, we have nitrogen combining with hydrogen gas to produce ammonia. So in this instance, the equilibrium constant would be equal to the concentration of ammonia squared divided by the concentration of N times the concentration of H cubed. Remember that this is only for when the reaction is at equilibrium. If the reaction is not at equilibrium, this does not work, and this becomes something different that we'll talk about in a later video. So let's take a look at this practice problem here. It says to just simply write the equilibrium expression for Kc for the following reactions. Well, let's start off with A. So remember that our equilibrium expression is products over my reactants, and that the coefficient becomes an exponent. So for A, we're going to take the concentration of O2, we're going to cube it, and we're going to divide by the concentration of O3 and square it. It's pretty simple on how to go through and do these. Let's look at the next one. Again, concentration of your product. We're going to square that because it has a coefficient of 2. NO. Again, we're going to put a 2 there because, again, that's coefficient. And chlorine as well. All right, last one here. A little bit more complex chemicals, but the concept is exactly the same. All right, pretty straightforward there. And now what's nice is if we know that, let's say this bottom one here is equal to KEQ, okay, or KC, then we can plug in numbers and solve. Okay, if we know the concentrations of the others at equilibrium, we can solve for the other one, or if we know those concentrations, we can solve for KEQ. So this does become a mathematical expression. Okay, pretty straightforward here. Let's move on. Now, when we've looked at this, we've looked at things that are aqueous and things that are gases. The same concept can be actually applied when dealing with gases and substituting pressure rather than concentration. The concept still works here. So if we know the pressures of all of the different gases, and we know the coefficients of all of them in the balanced chemical equation, we can solve for Kp, equilibrium constant of pressure. The one thing I would suggest here is to be careful when you're looking at pressure changes as we go from, or we go towards equilibrium. So let's use an example down below. We have CoCl2 being converted into carbon monoxide and chlorine gas. The pressure starts at 1 atm, and let's say it finishes at 1.2 atm. Remember that for 1 mole of CoCl2, you produce twice as much product, right? 1 mole of CoCl2 is going to produce 1 mole of CO and 1 of Cl. That means that the pressure of each needs to be considered. So we really need to think deeply about this in order to figure out what the pressure of each is going to be at 1.2 atm. Because it is becoming two separate things, we need to really think about this. So what you find out is that at equilibrium, you have 0.8 atm is the pressure of CoCl2, 0.2 atm for CO, and 0.2 atm for Cl2. We have to remember that the 0.2 atmospheres of pressure that's lost by CoCl2 becomes 0.2 for CO and 0.2 for Cl2, okay? So you need to think about how we're going to lose that 0.2 to be able to add them up to equal 1.2 atm, and when you add all those up, you get 1.2. So just be very careful and be aware of that as you go through and calculate some of those things. So what does the value of K even mean? We're calculating this constant. How does this help us figure out which direction the reaction proceeds? Well, the value for K actually tells us a lot about how the reaction takes place, and more specifically where equilibrium lies. If K is greater than 1, then the equilibrium lies to the right and the products will be predominant. If the K is less than 1, then the equilibrium lies to the left and the reactants dominate. Now remember, these are rates at equilibrium, not concentrations. Very large K values indicate that the reaction will almost always go to completion, while very small K values means that the reactants occur very little. Now what we'll learn about Le Chatelier's principle, which tells us a little bit about how we can force the reactions to go a certain direction based on different factors that we can influence the chemical reaction. So let's talk about calculating or finding the equilibrium constant equation for heterogeneous equilibria. Most equilibria exist as a gas or aqueous. However, when a pure solid or liquid is included in the equation, it is not included in the equilibrium expression. So for example here, we're going to calculate the equilibrium constant for Kc or KEQ for each of the following reactions. So this one here, when we calculate this, we do not include anything that is a liquid, okay, or a solid. So it has to be gas or it has to be aqueous. So for this one, we'll call this A. Remember that it is products over reactants, so the concentration of CO divided by the concentration of carbon dioxide and hydrogen gas. Okay. For B, same concept here. We're going to eliminate anything that is not a gas or aqueous. So what we're going to get is CO, concentration of CO2. Remember, coefficients become exponents. Just like that, all right? Pretty straightforward here, but do keep in mind that when a pure solid or liquid is included in the equation, it is not included in the equilibrium expression. A mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at 472 degrees Celsius. The equilibrium mixture of gases was analyzed and found to contain 7.38 atm of hydrogen, 2.46 atmospheres of nitrogen, and 0.166 atm of NH3. For these data, calculate the equilibrium constant for the reaction. So our first step here is to actually write out the equilibrium expression. So we're going to start with Kp. And we're going to set that equal to the concentration of NH3 squared over concentration of N2 times H2 cubed. And what we're going to do is we're just going to simply plug in. Remember, atmospheres, units of pressure, can work exactly the same as the molarity concentration. So we can plug those numbers in and solve very easily for Kp. So Kp is going to equal, got NH3, so it's going to be 0.166 squared divided by, put these in brackets, 2.46 times 7.38 cubed. And we just simply plug these into our calculator and solve. We get 2.79 times 10 to the negative fifth. Okay. There are no units on the equilibrium constants. Okay. So do keep that in mind, but pretty straightforward how to solve these. But might be a little bit more complex if, let's say, we're looking for the value of one of the concentrations. So let's take a look at one of those problems. For the Haber process, which we've talked about quite a bit, Kp is 1.45 times 10 to the negative fifth at 500 degrees Celsius. In an equilibrium mixture of the three gases at 500 degrees Celsius, the partial pressure of hydrogen is 0.928 atm, and that of nitrogen is 0.432. What is the partial pressure of NH3 in this equilibrium mixture? I know part of it's cut off, I'm sorry, but hopefully you're listening. So the first thing we need to do is, again, set up our equilibrium expression. So Kp equals NH3 squared divided by N2 times H2 cubed. So in this problem, we're given the partial pressure of H, nitrogen, and Kp. So now we have to solve for NH3. So let's do a little bit of algebra here. So we're going to have 1.45 times 10 to the negative fifth set equal to our unknown value, x squared, divided by N2, 0.432, times H2. And we're going to cube that. Now, the rest of this algebra is pretty straightforward. We're going to multiply by the denominator on both sides. So what we're going to get is x squared equals 1.45 times 10 to the negative fifth multiplied by 4.32 times 0.928 cubed. Multiply all those numbers together. Remember that in order to get out a square, you have to take the square root, the whole thing. What you find is x is going to equal 2.24 times 10 to the negative third. Now remember, when we solve for x here, we're looking at the partial pressure, so this needs to be an ATM. All right. Pretty straightforward on how to go through and do that as well. So let's move on to one more type of problem, and we'll go from there. A 1 liter flask is filled with 1 mole of H2, 2 moles of I2 at 448 degrees Celsius. The value of the equilibrium constant, Kc, is at 448 degrees Celsius is 50.5. What are the equilibrium concentrations of H2, I2, and HI in moles per liter? Now, the difference between this problem and the problems we've looked at previously is that this gives you our initial values. These values are not at equilibrium. So we need to find out what the values are at equilibrium to figure out, well, what the values are at equilibrium. I pretty much just said that. So in order to do this, we need to figure out how much these things are going to change. That becomes a little bit complex. So what we need to do here is I would start off by writing my equation and writing out my initial concentrations. So we're going to start with H2 plus I2 yields 2HI. Okay? And we're going to start with our initial concentrations. Our initial concentration is 1 mole and 2 moles. Okay? And again, these are our molarity concentrations because it's in a 1 liter flask. So we need to make sure that we're good with that. These are all molarities, they're concentrations. And we start with none of this. Change. So how do we know how much change is going to happen? Well, that really is our unknown. Once we figure out how much something's changed, we can calculate the equilibrium concentrations. So as the reaction proceeds, we have all reactants and no products. So what's going to happen here is we are going to lose X amount of H. Because these are the same mole ratios of our coefficients, we're going to lose this much, all right? And because we get twice as much product, we're going to gain that much to become product, okay? So we have to think about how much we are going to lose versus how much we are going to gain in this reaction. And by doing that, we will call that X. So now we have formulas for our concentrations at equilibrium. This is 1.00 minus X. This is 2.00 minus X. And this is 2X. Well, now let's plug those into our equilibrium constant expression. Okay, EQ here is going to equal HI squared over H2 times I2. Okay? So we can plug these values in for there and actually solve for X. This is where this gets complicated because you're going to have a lot of squares in there, and you're probably going to have to use the quadratic formula to be able to solve for X. So 50.5 equals 2x squared divided by 1 minus x times 2 minus x. Okay? And then again, you would FOIL the bottom, you'd FOIL the denominator. Now, if you have an equation solving calculator, you can actually immediately solve for x with this. If not, you're going to have to use the quadratic formula. This is where this gets a little bit nasty, okay? Because after squaring everything out and multiplying, what we're going to get and again, we work through to simplify this expression as best we can. And now that we have A, B, and C, we can plug those into the quadratic formula. And what we end up finding is that x is either 2.323 or 0.35. So now that we have x, we can go back to our equilibrium expressions. Remember, H2, the concentration at equilibrium, was equal to 1.00 minus x. I2 was 2.00 minus x. And HI was 2x. So if we look here, one of these two answers is going to be correct. It can't be this one because we can't have a negative concentration. So what we do is we plug in 0.935 for each x, and that will tell us the equilibrium concentrations for all three. So we have h squared 0.065, I2 1.065, and HI, because it is doubled, 1.87 moles per liter. Okay, so again, when we are given the concentrations at the beginning and we're solving for the concentrations at equilibrium, we must do an ICE table. Start with your initial, figure out what is changing, and then determine what's at equilibrium. Plug that into the equilibrium expression and solve. You may need to use the quadratic formula in order to be able to solve some of those problems. All right, let's move on. So lots of stuff going on in this video. Just make sure that you're able to understand how to go through some of those calculations, look and see what's given to you. The key thing here, make sure you know how to write that equilibrium expression correctly. So that way we can calculate KEQ, KP, KC, all that good stuff. All right, we'll talk more about ICE tables in class. Have a great day, guys. We will talk to you later. Bye-bye.